Morning, everybody. I'm just going to run and grab my headphones. Just one second. All right, I'm back. I forgot to have my headphones on. We're gonna get a little bit of feedback noise from the printer. Welcome back, everybody. So today we are talking about equilibrium. I think. So up until this point, we've been talking about reaction rates, and you'll be getting an assignment on reaction rates pretty soon. But now we're going to move over to chemical equilibrium. So before we get that far, let's use this little blank page here, because I would like to propose an idea to you. If a chemical reaction, if the rate of a chemical reaction depends on, so if a chemical reaction depends on concentration, right? So in the rate law, we said that the rate of a chemical reaction is equal to K times the concentration. All right. So in this case, this means that rate depends on concentration. Well, over the life of a reaction, right? Over time, the concentration of a reactant goes down. And we said that because the rate of reaction slows, so will the curve of this graph slow. So over time, the graph has to slow down. So this is our reagent, right? But if the concentration of the reactant is slowing down, then doesn't that mean that there's a concentration of product? And so if we think about the product, we had no product before, and then the product is increasing. So the concentration of the product is increasing at some point. At first, there's going to be very little product, right? And then there'll start to be more and more product. Well, more and more product means the concentration of the product over time is going higher. So we're starting with no product, we're having an increase in product. What's going to happen to the rate of product? Or the rate of reaction in terms of product? How much product are we going to get as the reaction slows? I suppose at the very least we know that the amount of product will have to slow since the chemical reaction is slower here. We know that the amount of product should be slower there as well. And it'll turn out that we're going to be looking for something that looks like this. Right? Yeah. And so that's what this graph is showing us here, is this kind of reaction, at least from this point on. You can see the consumption, the creation of H2 gas through the consumption of NH3 and the production of N2. And so these have complementary rates and speeds. So that's from the formation of the gas. And this state at the end here, where the amount of gas, or the amount of gas being produced, and the amount of product, this is product, the amount of product being used, and the amount of reactant being used up, and the amount of product. Yes, this is the new unit. Yeah, as I mentioned in the stream yesterday, we are moving to the next unit. We finished the reaction rate yesterday, so we're moving into equilibrium. And I posted the booklet this morning. All right, so let's move on to the first lesson of this booklet. We're going to talk about equilibrium. This is that state at the end of that graphic there, where the amount of reactant being used up and the amount of product being formed is slowing down to a steady state. So there are a couple of different types of equilibrium that can happen. One case is physical equilibrium. So in the case of a physical equilibrium, there is substances are undergoing physical changes like phase changes, liquid to gas, gas to liquid, and those two physical changes are occurring at similar or identical rates. So whenever you have a glass of, whenever I have this sort of sealed container of water, inside the sealed container of water, there's a certain amount of water in there. There's a certain amount of water vapor in there. And the water vapor and the water in the water are actually constantly exchanging water molecules. And those water molecules are exchanging at about the same rate, so that any point in time when I open the bottle and I look inside, it seems to have about the same amount of water vapor and the same amount of liquid. Now, this would be a little different if I could take my vacuum or something, vacuum out all the water, close the lid really tightly. Suddenly, there'd be lots of space in the air above. There'd be no water vapor, no gas particles, and so the water would expand very rapidly to fill in that space. And so then the rate of reaction for liquid turning into gas would be very fast, very high, and until we got to a point where they were in equilibrium with each other. Now that I see that we've got a couple people on there, is there any interest in moving the stream to later in the day? I do have a time slot at 11 to 12 that we could run the class. So let me know what you think about that. I'm just going to put a comment in there. Would you prefer a stream at 11 instead of 9? Okay, so let me know what you think. I'm really happy to see that we've got quite a few viewers today. So we've actually got 5 of us out there instead of where we were a couple days ago. So great to see that. All right, so what else do I have to say from here? So in this case, it's a physical equilibrium because, good to know. Yeah, it's physical equilibrium. So the last two live streams were finishing up the previous unit. This is the first one for the new unit, which was just posted this morning, because I wanted, anyways. So, for example, once the container reaches equilibrium, the total number of vapor molecules will remain constant. So when we're talking about physical equilibrium, we're talking about a dynamic system because of moving particles and moving molecules, and this will there's no actual chemical change. So this is moving between states. So we're not talking about no chemical change. Just physical states. This is not the case if you take a piece of ice and throw it in a cup of water, right? So in the case of ice and water, the ice will start to break apart. It starts to melt. It is undergoing a physical change, and it's not at equilibrium. But if you put in enough ice into something, you'll actually bring the water down to about 0 degrees Celsius, and the water and ice mixture will have very little exchange. Will have very slow exchange between the ice and water states. There'll still be some changing. You'll actually be taking some of the water molecules, some of the liquid water molecules will actually be becoming part of that ice over that time. Now let's talk about equilibrium in terms of chemical. This is the one we're going to talk about most of the time. So chemical equilibrium occurs when the forward and reverse reactions are taking place at the same rate. So this is where I wanted to think about what was happening in our previous unit. So in our previous unit, we said that rate was equal to K times the concentration. So let's just call this one forward, and this one will be reactant. So let's say we had like A turning into B, okay? Over time, as this chemical reaction happens, you are producing B, right? So that means that you are producing B. So if you had a reverse reaction, if you said this reaction was reversible, if you said the reaction was reversible, then we would say that there is a reaction that goes backwards as well. This is product. And as the reaction goes forward, right, over time, you're going to be producing B, right? So B is increasing. So that means that the speed, that the rate of reaction is going up. So rate of B is going up. Or the rate of reverse is going up. And as you, over time, the amount of A is decreasing. So then the rate of A is going down. So that's really interesting because it seems that at some point the rates will become equal. And in fact, if we plot out this graph, but now plot it with rate instead, so if we did time and rate, we would find the graphs go towards the same rate, so that A and B have the same rate of formation, or forward and reverse have the same rate. So here's the forward one slowing down, and here is the reverse reaction speeding up. This really only applies to a closed system. So I feel like we mentioned closed systems before, but we're going to mention them again now. So closed systems are ones where we are going to assume that no particles can exchange. a system where no matter can be exchanged with the surroundings. Now, do we say, is it energy as well? Yeah, it's an energy of transfers off. Just going to check an equilibrium. Oh yeah, energy still to be taken out. All right, so I suppose tomorrow we will start our live stream at 11. It looks like. I'm going to post our link here just because I realized I didn't post that either. How's everybody doing out there? Keeping busy? Okay. Previously, we assumed that reactions proceed completely from the reactants to the products. However, many chemical processes are reversible and proceed in both the forward and reverse directions. There is some theory that every reaction is reversible, but very, very difficult to reverse. But in general, there's a category of reactions that are easily reversible, and there's a category of reactions that are very difficult. Yeah, that sounds about right, yeah. So let's consider the conversion of nitrogen dioxide, NO2, into nitrogen tetraoxide. So this is a really interesting reaction because it produces a dark brown gas, and it's part of smog. So when you see that sort of brown haze in over cities, as particularly in the news, we don't get that as much in Manitoba because of our strong winds. But something even like Toronto or New York will have this sort of brown haze, and that is somewhat caused by nitrogen dioxide. The brownish color tint is from the presence of nitrogen dioxide. It's brown, while dinitrogen tetraoxide is colorless. If nitrogen dioxide is placed in a sealed container, eventually the brown color fades, but not completely. So I will look up an example of that. You can watch a video of it on your own time. Let me cue that up. Nitro. Oh, tetroxide. Yeah, this one here. So if you want to watch this this video, I recommend it. I'm going to put it in the comments here. So this is a sealed container of nitrogen tetraoxide, and they apply different amounts of temperature, which shifts the equilibrium between the two gases. both gases are present at any given time, but if you don't have enough of the brown gas, of the nitrogen dioxide, then it does not appear brown. And so we can manipulate that equilibrium and make it go back and forth all day long. So this the equilibrium state is characterized by constant concentrations of both the reactants and products. This is constant concentrations, not equal concentrations. So they do not have to be equal. Not equal. Only constant. Even your DNA has this sort of aspect where DNA is generally two strands that are connected together, but they do have the ability to go to open and close, and that opens up all the possibilities of things like reproduction of the DNA for mitosis and all those other processes. So it's a reversible reaction, a reaction that can change its arrangement and rechange. So this reaction is then written as add 2NO2 and then the equilibrium arrows. So these are the equilibrium arrows. Equilibrium arrows to the other ones. The equilibrium state is dynamic since both the forward and reverse reactions occur simultaneously. We used the word dynamic before when we talked about thermodynamics, or the idea that there was dynamics in energy movement inside of a system. So this is the same idea. Equilibrium state is dynamic, so this means that they're both occurring simultaneously. Constant interchange. I don't know if I'm going to say anything there. Let's just get rid of that. That's okay. Now the equilibrium arrows, they come in a couple of varieties. There is an equilibrium arrows that are even like so. You might also have the arrows so that the top one is a little bit bigger, or the arrows where the top one is small and the bottom one is bigger. And so this one simply means that the rates when the rates are equal, that both the products and reactants are equally favored. This one in the middle, the products are favored, but there is some reverse reaction happening. This the last one is that there is a little tiny bit of forward reaction, but mostly the reaction favors the reverse. We'll get into that in a second. So here's those images that we were drawing earlier. As the reactants get used up, you start to produce product, and the amount of product increases. Ooh, excuse me. You got some coffee in there. Okay, so if we plot the concentration versus time, the product in the equilibrium system, it will appear as below. Here we see the formation of products at the cost of reactants. We could have two different setups here. Notice in this first example, we reach chemical equilibrium with a high amount of product. In the second example, we reach chemical equilibrium with a low amount of product. So we could probably define these with those arrows that I was kind of throwing around up top. In this case, it looks, they're not quite, the dynamic equilibrium is a little bit more favored towards the product side and a little less to the reactant. So this is an example of that. A reaction that favors products. Reaction favors products. And then over here we have a reaction that does not favor the product. So we have more of the reverse process probably happening. So favor And many different reactions have very many different processes or different balancing. Almost every reaction has, I guess, its unique balance. And as chemists, one of our goals would be to see if we can convert those unique processes, or if we could affect that unique balancing act. Is there ways that we could push the chemical equilibrium to be more product favored in, say, this example number 2? So once equilibrium is reached, the concentrations of the reactants of the products remain constant indefinitely. So unless there's a change to the system, typically a change through adding more energy or changing the volume, if there's no change to the system, then the system should stay at equilibrium forever, pretty much. Notice the concentration of products and reactants are not necessarily equal. If we graph the rate and time, it would appear as below. So let's go with time and rate. Sounds good. I think 11 is going to be maybe will win us all that attendance I've been looking for. It was my break, but I think I can make that change. That's no problem at all. Yes, okay, that's what I thought. So the interesting thing here is that the rate of reaction for the forward reaction is going to be slowing down. So the forward reaction will begin to slow down, like so. So this is the rate of forward. And so it begins quickly. This is the one I don't like, is that when I think about, if I think about the rate of the reverse reaction, I feel like the rate of the reverse reaction actually should be, but I'm looking at the graphs and they bug me, but that's okay. Yeah, okay. All right, it's pretty consistent. So, all right, let's give it a look. We have, so the rate of the reverse reaction is also going to slow down over time until it joins them. Wait a second, doesn't that seem like rate of a reaction is dependent on concentration? So shouldn't the rate of the reverse reaction be the rate of the forward reaction be slowing down? Oh yeah, okay, I got them backwards. Oh, whew. Okay, I knew I was like, I knew there was something bugging me. So think about it like this, yeah, okay, this is better. All right, so this is the forward reaction. Because over time, the forward reaction is losing concentration, right? So for the rate is equal to K times the reactant. So for rate of the forward reaction is equal to K of the reactant is going down, so the rate should be going down. So that's why the green one is going down. If we do the other plot, which is our rate of our reverse reaction, which would be equal to K times our product, well, as the reaction proceeds, the amount of product is increasing. And so we find that the rate is increasing. And so that's what we're seeing here, is an increase of the rate with the increasing amount of product that's formed, and the other one is the decrease in rate as the amount of reactant is consumed. So let's just write that out in a little text box here. So as reactant is consumed, the rate of the forward reaction decreases. And I'm going to put that all in green to match. As the product is formed, the rate of reverse reaction increases. And then the important part here is that as the two rates become similar, the concentrations no longer change, so the rate stabilizes, become equal. So that's a pretty tricky concept. I will give you that. This initial idea can be a challenge to wrap your head around. So make sure you spend a couple of seconds thinking about this. So as the reactant is consumed, the rate of the forward reaction decreases. I hope we can wrap our head around that idea. As the product is formed, the rate of the reaction for the reverse reaction increases. So you start with 0 product, and then as you get more product, then the reaction rate for the reverse reaction starts to increase. Once the two rates become similar, then the concentrations will no longer change because the rate of the forward production and the rate of the reverse production are equal. You can see my 3D printer going now. I was hoping to get some spectrophotometers working for you all, but I'm not sure what the future holds for us. But I'm hopeful. I'm hopeful that we're maybe if we're not going to get back to class, at least we're going to have a lot of fun online. And I'm wondering also about doing a class meeting, or maybe one of my jobs has been doing a coffee time, so or a coffee, what do they call it? A coffee meeting, I guess. Coffee break. That's it. And they just they open up a chat room on like Google Meet or something, and then just allow students well, in this case faculty, to join up and just have a little informal meeting. I was wondering about sort of running some of that, maybe essentially my resource time, and so I'll see about setting that up. It'll be probably through Google Meets, or yeah, Google Meet. All right, so equilibrium law. This is the math part. So of course, I hope you were enjoying math already, but all the math, because now we're going to do some more. So equilibrium law is a mathematical description of a chemical system at equilibrium. So once the rate of consumption and production near each other, the concentrations become stable. Yeah, that's right. Great. Okay, so in equilibrium law, we have a mathematical description that explains this idea. And it's really simple, actually. All we're going to do is we're going to use a rate law for a forward reaction and a rate law for a reverse reaction. And that's it. We're just going to take both the forward and reverse rate laws and then use this statement we just made that at equilibrium, the rates of the forward and reverse reactions are equal. So here, if the forward and reverse rates were elementary reactions, the rate laws for the forward and reverse reactions would be. So if we have some sort of reaction like this, where we have A, A, B, and C and D, then we could say that the rate of the forward would be equal to K, and let's put a little FW, times A to the power of A times B to the power of B. And by that same token, we could create a similar reaction where we say that the rate of the reverse of rev is equal to K of the reverse C power of C D to the power of D. How do you feel about that? Does that statement seem to make sense? I haven't said anything too exciting yet. Anybody see where I'm going to go for the next step? What assumption did we just say at equilibrium? At equilibrium, we suggested that the rate of the forward and the rate of the reverse are equal. So at equilibrium, rate forward equals rate reverse. So by the rules, by mathematical substitution, we can say that this part, I missed the W here. This forward reaction is equal to this reverse reaction. At equilibrium. So this becomes the equilibrium law in a way. We have a little bit of manipulation to be done here, but which we're going to get into in a second. But I just want you to ruminate on this this conclusion. If the rate of the forward reaction is equal to some constant times the two forward reactants, and the rate of the reverse reaction is equal to some constant times the two reactants, then those two rates those two equations can be made equal to each other at the point of equilibrium. From this conclusion, we can play with this just like it's any regular equation. And a really useful thing to do is to reorganize the law so that the products are over the reactants. And so I'm going to do a little bit of reorganizing. I'm going to make another copy of this, and then I'm going to manipulate it. Duplicate. Clean up that there. And all of this is getting too big for me, so I'm going to have to shrink it all. Okay. All right. So what we're going to do is we're going to take the reverse. We're going to take the values of concentration and we're going to move those over into the denominator. And we're going to move our k's over together on the other side so that we can create, because k's are constant, that makes them useful. So we're going to leave those all on one side. Now this whole thing over here, this is all constant, right? This is a constant divided by a constant. So it's never going to change. So let's just get rid of that altogether and make a new value, a new constant that is also never going to change. So we're going to write KEQ, and I believe that K is capital now. So before we had a lowercase k, now we have a capital K. I believe so. And that's to represent that we have two smaller reactants, our reaction equilibriums being converted. Okay. I'm going to do a little bit of cleaning up to kind of give us a nice, something nice for you folks at home. All right, I'm going to just bring this all over here. No, I don't want to do that. Let's just get this out of the way. That's it, equals. So we have created a much more complicated looking equation, certainly. It has more variables, so this is one of the reasons we do this second to the rate law. So if you found rate law to be a little bit confusing, then this can be a little bit more trouble because we have so many variables, and it will actually cause us a little bit of headache later when we have to, solve for things that are raised to multiple powers and all that sort of stuff. But we can do it. I believe in you. So this KEQ, this is the equilibrium constant, and what it's telling us is this thing tells us the ratio of concentration for concentration product to reactant at equilibrium. Now, assuming that all reactions are going to eventually reach equilibrium, this K value could be very powerful. If you have a good understanding of K, then looking at any reaction, just eyeballing it and saying, "Oh, the K is 10 to the power of 20? Wow, that must be a lot of product you're making." If someone tells you that the K is 10 to the power of -5, you go, "Ooh, I don't know, that reaction doesn't seem very good. It doesn't seem to be producing a lot of product." So homogeneous equilibria are those in which the reactants and products are all in the same phase. This is the more straightforward case. So this is almost all the time that we're going to do these kind of problems. We're going to probably deal with homogeneous equilibria. It applies where everything in the equilibrium mixture is in the gas phase, or everything is present in the aqueous phase, the dissolved phase. And so those reactions are going to be, those reactions will just be straightforward. We're going to take all of the reactants and all of the products, put them into this format, and then raise them to the power of their coefficients. So products go on top. So I'm going to put my NH3 on top. And I'm going to raise it to the coefficient 2. I'm going to then divide by the concentration of the products, of the reactants. So down here, raise it to any coefficients, there's none, so I leave it blank. Raise it to any coefficients, there's a 3, so I'm going to go H2 to the power of 3. All of this will be equal to some K that I don't know. It has to be given to you, or you have to determine it using experiments. So we're just going to call it KEQ. And that's it. This is the equilibrium law. Equilibrium law. For this reaction. If you're in a situation where the equilibrium is between chemicals that are in different phases, then we have a problem. So when writing the equilibrium law for substances that are solid or liquid, we ignore those solids and liquids. It's the assumption that a solid or liquid has a much higher density and much higher concentration, or not concentration, doesn't really have a concentration. That's kind of the problem. So a solid doesn't have a concentration. It's a solid. It's all there. So if the solid is present, it's in it. The measurement of how much of it is in a different is done in a different way. That's not compatible with the equilibrium. Pure solids and liquids are not included in the equilibrium constant. This is a classic place where teachers will trick you. This is the tricking place. We will place a solid or place a liquid in the equation, ask you to draw out the equilibrium law, and what we're looking for is for you to not include something. So in this example, we see that there is solid carbon. I'm trying to trick you. I'm trying to see if you'll put carbon in your reaction or in your equilibrium law, and hopefully you won't. So you're just going to put the products and the on top. So products, always product over reactant equals KEQ. Divided by the other reactant. Notice that there's that water here is in a gas, so it does have a concentration, but we do not include the carbon. And then don't forget your K. The next example is interesting. We have two solids. Both of them get ignored. Even though the one solid has a coefficient, it doesn't matter. All that matters here is we're going to only care about the relationship between the concentration, the chemicals that have concentration. Now notice that I need to include this too, so I'm going to include that as an exponent. So for this last one here, for B, KQ is going to represent the ratio between copper ions and silver ions in a solution that has reached equilibrium that has copper and silver. This is the classic silver tree experiment. If you've never seen a silver tree, it's really quite fun. There was a professor at U of M who always made these silver trees. If you just type silver tree, there's a whole bunch of like examples, but let's see if this one will, if I can just share this. No, that's not what I want. Just go on YouTube and you can find all of the silver trees you could imagine. It's a pretty classic example. You just need some silver nitrate and some copper. As my professor in U of M would say, it's sort of a wasteful experiment because actually you're getting pure silver out, but pure silver is cheaper than silver nitrate. So you start with expensive silver nitrate and some copper. Copper is relatively inexpensive, I guess, but you end up producing some completely worthless copper nitrate and some pure silver, which has less value than the silver nitrate that you just used to make it. But it's still fun and it's still interesting. Here, let's drop a little silver tree on here. Silver. There we go. So that's what the silver tree looks like. You can see it sort of growing in that vial there. So it's very fun. Okay, so the last one is the trickiest one, and I have had many a student make a mistake on this one. It's products over reactants. Actually, there's a reverse reaction of this that is even trickier. It's products over reactants. So we were talking about CO2, and that's it. There are no products, no reactants here. I mean, I suppose you could put a 1 to just say that there's none, but we have no product. Now, I would say that an even more sneaky version of this is someone who writes out CaO solid plus CO2 gas and says that those go to form CaCO3 solid, because for this expression you're going to do products over reactants, so you actually have to put 1 over the reactant, and the only reactant that has a concentration is CO2. And so that would be the result. If you think about it, these two KQs are actually going to be, let's just do a little thought bubble here, that this KQ has to be equal to this KQ to the power of -1, because that's the inverse of the reactions. That's just a little side. If you invert a reaction, you'll get the inversion of the equilibrium constant. Okay, this keeps going for a little bit. Oh, there's some practice here. Okay, well, I think we can get these last 2 pages done in the next 5 minutes. Let's see how we do. So the equilibrium constant, we've already discussed this one. This is equilibrium constant is a constant that represents the ratio between the concentration of reactants and products at equilibrium. And so by those cases, if the equilibrium is equal to 1, then the products and reactants are equal. So we have about the same amount of product and about the same amount of reactant with some exponents raised in there, but the concentrations are going to be equal. Neither reactants or products are favored, and this is where we use that equilibrium arrow that is equal in both arrows. If the KQ is very big, if it's larger than 1, then we're going to say that the product is greater than the reactant. And so another way of saying this is that the equilibrium position lies to the right. So this is a favorable reaction as well. This is favorable. So when we're comparing two experiments, one that has a high K is going to have it be considered a favorable reaction, something we want to happen. This is a reactance is favorable reaction, so when K is less than 1, and so that is bad news. This means like an unfavorable reaction. usually a slow reaction. There are lots of uses for unfavorable reactions. For example, we can use a high equilibrium value like the reaction between phosphates and lead. So when the city will often pump potassium phosphate or an orthophosphate into your water supply, especially if you live in one of the neighborhoods with lead in their pipes. This phosphate will go into the water supply. It'll react very favorably with lead and form lead phosphates. Those lead phosphates then have a very low equilibrium with water, so they can't dissolve. So we form insoluble lead phosphates, and those insoluble lead phosphates stick to the side of your pipes, and they keep the lead from entering your water supply. Now, this is all based on doing experiments at one temperature. If you change the temperature, you change the equilibrium constant, you change the position of the equilibrium, because you create a situation where one of the reactions is going to get faster, one of the reactions will get slower. Remember that we are thinking about, we have to keep in the back of our mind this potential energy diagram situation. So in this case, if temperature goes up, then we're going to favor one of the reactions. In fact, if we don't want, I don't want to get into that yet. We'll get into that next, but think about how these are not equal. The two reactions, the reactions do not have equal correlations with equal dependence. Yeah, let's go with dependence. And temperature. So I'm going to let you think about that one. Which reaction does get faster? Is it the reverse reaction or the forward reaction that gets faster in this situation? If if this is forward and this is reverse, which reaction benefits from an increase in temperature? Something to think about. And that will cause a big change in your K. All right, so we have some example questions to follow, so please do those today. And tomorrow we will see you at 11 for our class, and we will get into lesson number 2. I also have been preparing a online form test for kinetics. So we're just going to go ahead and go under the assumption that we can complete this course online. So I am going to start doing things like tests and stuff. Of course, tomorrow's Friday before spring break. You are entitled to your spring break. So we will take that break at that time, and I will probably go back and fill in some of the kinetics videos with those sort of more shorter, concentrated videos. Anyways, I do have to get another class started right away, so hope everything's going well for you out there. Stay positive, stay safe, stay home. Wash your hands, all that stuff. And I'm looking forward to seeing you all tomorrow at 11. Thank you.